Hello, welcome. This is my video for audio electronics about standing waves and other such joyful things involving them. If you're watching this video and thinking this is really nerdy, then you're not Justin Riley. So my name is Corey Carter, and I'm here to talk to you about standing waves today. First of all, a standing wave is essentially when there are rooms with parallel walls and there is a frequency that is produced that ends up being more prominent than the other frequencies in a series of overtones. In a series of the 12-note scales too. So any frequency you can think of, there is a mathematical equation to go from this wall with the EA Sports poster to this wall with the Inglorious Bastards poster. That based on the length that these two walls are apart, if it hits this wall straight on, bounces to that wall, hits it straight on, and then comes straight back, then it will basically just continually cancel itself out and then amplify itself over and over again. How this happens, got this handy piece of paper here. Got a wave, right? And this wave is traveling in this direction, that way direction, and it's going to hit this wall. So wall, and then bounce back, and because sorry, excuse me, I'm not an artist. It basically comes back in the same direction. There, that right there is a good example. From here over, so we'll ignore the rest of this. So these are the peaks of both waves, and these are the troughs, and as you can see, they cross at both points. Now what happens when these two waves, when their crests occur at the same time as this wave is being produced, these two actually will amplify each other, and you end up getting a wave that looks more like this. See how this is larger because they amplify each other. Now what's crazy about this is when both of these midpoints intersect, well, crest trough, when these flat lines intersect, they actually are canceling each other out, and the frequency is not really audibly heard at all. So this area cancels out. Now when these standing waves make it to this point and are doubly amplified by each other, this is called an antinode. Antinode. And when they are at the same point to where they've canceled each other out and there's nothing heard at all, this is called a node. So a node is, if I were to stand here and play A440 and wouldn't really be able to hear it because it canceled itself out, let's just say that the standing wave for this room is A440, then we wouldn't be able to hear it. And then if I were to stand maybe a little farther over here, I would maybe get the antinode. Let's say it's a fourth. Let's say it's whatever the hertz value of D above A440 is. Right here might be extremely resonant here in the room and doubly pronounced because it is being amplified by A440's waves. So that's how that works. And now we're going to look at this lovely room and try and calculate what the resonant frequencies of this room will be. Now, normally you would have to take some sort of obnoxiously long measuring device to measure a room this big, but Capital University has kindly placed some tiles on the floor. Now these tiles are exactly 1 foot in length, and I've checked this with the university website because it actually gives, as we'll show right here, the dimensions of the room that we're in. So that would be Sailor Ackerman rooms. Alright, it says 12 by 16. Alright, we'll take their word for it. But if you want to be sure, we're going to count these squares now. 1, 2, 3, we come over here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so there's our 15. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, continuing over here, 10, 11, 12. Alright. Now there's a little extra space over here by the door, behind the wall, so that gives us our 16 by 12 measurement. And then we're going to use an awesome technique that I know how to use to measure the heights of things. I have taken one of these shoes here, and they are, as you can see, exactly 1 foot in length. So we have a shoe propped up against the wall. Now we're going to back off, like so. We're going to take our thumb, stick it out right in front of us at arm's length, and back up so that it is exactly the same height as the shoe, and then just continuously put our thumb on top of itself in our mind's eye, like so, and we're going to measure the height of the ceiling. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so this is a 9-foot ceiling, which it just happens to be. Now that we've got our measurements, we'll come over here where these measurements are already taken down, and we're going to do some math. Now, with the assumption that this room is a perfectly square room, I mean the walls are perfectly straight at 68 degrees Fahrenheit, we know that the speed of sound is 1130 feet per second. So we have 1130. We're going to divide that by each one of these lengths to get a frequency, or the lambda symbol for wavelength, in hertz, and we'll get 3 different frequencies for each one of these walls. Alright, so 1130 divided by 15, 1130 divided by 12, and 1130 divided by 9. Alright, so we'll go get our handy dandy calculator, since we are music majors and not math majors. And quite honestly, it's been so long since I've had to do long division. I think before I was able to grow facial hair. This calculator's dead. Okay, guess we're doing it the long way. 1130 by 15. Alright, so we'll take the 1 in here. 1130. Alright, 5, that's 370. 3.7 ohms. So 0.0. Keep on keeping on. 2. Tell you what. Obviously very inadequate in the math department. Hello, MacBook. Finder, please do an operation for us. Alright, 1130 divided by 15 equals 75.3 repeating. So 75 and a third. So 75.3 repeating. Alright, let's come back over here and make this 12. 94.17 rounded. And divided by 9. 125.56. Okay, so 125.56 hertz, 94.17 hertz, and 75.33 hertz would all be very low frequencies, probably really hard to hear. So what we're going to do, one second here. Alright, we're back. Just had to check on the math to make sure, but we've discovered that this room has resonant frequencies of 125.56 hertz, 94.17 hertz, and 75.33 repeating hertz. So if we were to want to take out these resonant frequencies to kill their node and anti-node properties, basically those are really low frequencies, so we might consider putting in some bass traps or some diffusers, just depending. Obviously, I use a bass amp as an alarm clock, and I've never noticed it really being too bassy or anything in this room particularly. I've never noticed anything like lights rattling or fans falling off of dressers or anything. So what I would say is, if it's really a problem when you discover it on a recording, or if you were like mixing in here and listening back to this room, maybe you set up a couple of diffuser pads in between the area that you're miking. So maybe, let's say, miking here in the center of the room, and right there above the alarm clock, and maybe right there on the wall in between beds 2 and 3. By the way, this is bed 1. And yeah, that should take care of any funny things that you're hearing. Otherwise, you just should maybe reconsider how you're doing your EQ in your final mix. Alright, so I think that's just about everything I had to cover. Hope this video was of high quality standards and very informational. Peace.